Welcome to This Explainer. Today, we are popping the hood on the absolute workhorse of our modern world to look at the ultimate data factory blueprint. We're going to master the foundational engineering of the central processing unit. If you've ever found yourself wondering how a tiny little chip of silicon manages to coordinate billions of tasks a second without missing a single beat, well, you're in exactly the right place. We're going to decode this complex architecture together and translate all these high-level engineering concepts into a really clear visual roadmap.
Here is our mission briefing for today. We're covering 5 core areas: processor organization fundamentals, the instruction cycle, the power of pipelining, hardwired versus microprogrammed control units, and finally, mastering your CPU goals.
Let's jump right into Section 1, Processor Organization Fundamentals. So processor organization. You can really just think of this as the fundamental floor plan of our digital factory. Before any actual work gets done, you need to know exactly where the storage racks are, right? You need to know how the raw materials are packed and the precise routes your forklifts are going to take. In the CPU world, this means understanding how our registers, which are essentially these ultra-fast little storage workbenches, are organized to hold data exactly where the processor needs it the exact second it needs it. To really wrap our heads around this framework, we've got to talk about instruction sets. Basically, this is the native language, or the specific commands, that our factory workers actually understand. By analyzing machine instruction characteristics, we learn exactly what our CPU is physically capable of pulling off. And crucially, we need to dig into addressing modes. Think of addressing modes as the different strategies the CPU uses to actually hunt down data. Sometimes the data is handed right to it, almost like a tool placed directly in a worker's hand. Other times, it's just handed a map and told to go find it way out in the main memory warehouse.
Moving right along to Section 2, the instruction cycle.
You'll notice our processor structure flows really beautifully from the macro down to the micro. We start wide with the general processor organization, zoom in to identify the specific jobs of different registers, and finally we kick off the active instruction cycle. Now this cycle, it is literally the heartbeat of your computer. It's this relentless, non-stop loop of fetching an instruction from memory, decoding what on earth it actually means, and then executing it. Fetch, decode, execute. Over and over. We're talking millions or even billions of times a second.
But watching that cycle run, it naturally brings up a pretty massive engineering question. If our factory's assembly line processes just one single instruction entirely from start to finish before even looking at the next one, well, we're leaving a ridiculous amount of efficiency on the table, aren't we? So how do we push this machinery to its absolute limits without just physically cranking up the clock speed?
Which brings us perfectly to Section 3, the power of pipelining.
The answer is instruction pipelining, and it is an absolute game changer for performance. Instead of waiting for one instruction to completely finish up before starting the next one, pipelining overlaps them. So while instruction A is executing, instruction B is already being decoded, and instruction C is being fetched. It is quite literally Henry Ford's assembly line, but applied to digital logic. But of course, with great speed comes a catch. We have to mathematically measure those performance benefits and successfully navigate pipeline hazards. You know, those pesky moments when the assembly line jams up, maybe because one instruction desperately needs the result of a previous one that just isn't quite done yet. Managing those hazards, that's a massive part of modern CPU design.
All right, let's look at Section 4, hardwired versus microprogrammed.
Now this is where it gets incredibly cool, because we're looking at 2 totally different design philosophies for the control unit, aka the manager of our whole factory. On one side we have the hardwired control unit. This relies on state table methods and delay elements. We are talking physical logic gates wired directly together. It is blisteringly fast, but man is it inflexible. If you want to change how it works, you literally have to get in there and rewire the physical hardware. On the flip side, we have the microprogrammed control unit. Instead of physical wires calling all the shots, this unit focuses on sequencing and microoperations. It essentially runs its own tiny internal software program to figure out how to execute the main instructions. Sure, it's a tiny bit slower than hardwiring, but it is infinitely more flexible and so much easier to update or fix.
Let's bring it all together in Section 5, Mastering Your CPU Goals.
Let's take a quick look at this blueprint wrap-up checklist. Just look at how far we've come. You've gone from the big macro picture down to the micro. You can now summarize the core processor organization concepts and identify exactly what those registers do. We stepped up the complexity by throwing pipelining into the mix for that massive performance boost. And finally, you can break down hardwired control methods and even reach the point where you could identify the exact instructions needed to write your own microprogram. This right here is your comprehensive roadmap, taking you from raw foundational theory to actual actionable engineering knowledge. Because at the end of the day, every single milestone and every pipeline hazard we tackled on this factory tour, it all points back to one primary objective: giving you a rock-solid end-to-end understanding of how a central processing unit actually operates. We've traced the entire life cycle, from a lonely piece of data sitting in a register all the way up to the control unit directing the whole show.
But as you lock down these fundamentals and this architecture crystallizes in your mind, a whole new horizon starts to open up. Think about this as a fascinating little thread to pull on for your own self-learning. What kind of crazy new challenges and incredible efficiencies pop up when you introduce modern control units equipped with advanced CPU schedulers into this ultimate data factory? How does an operating system dynamically step in and tell this raw hardware what to prioritize on the fly? I'm going to leave you to ponder that one as you take these concepts and dive even deeper into the wild, ever-evolving world of computer architecture.